Thank you for having me at this year's EdgeSys workshop. My co-authors, Jonathan Hasenburg, David Bernbach, and I are with the Mobile Cloud Computing Research Group at TU Berlin and Einstein Center for Digital Future. And today I'm happy to briefly present some key insights from our paper towards a computing platform for the Leo Edge. You might not have heard of the Leo Edge before, so let me give a short introduction. There are a number of private companies out there that are currently building large satellite mega constellations in low Earth orbit, or LEO, which are used as communication networks. So low Earth orbit means altitudes of less than 2,000 kilometers. And these constellations comprise tens of thousands of satellites. And they are used as high bandwidth, low latency internet uplinks. So wherever fiber access isn't available, say in rural areas, on planes or cargo ships, small satellite dishes can be installed that connect to these constellations. And even if fiber access is available, satellite internet could still be a better option. That's because satellites have inter-satellite laser links between them. So the constellation provides a global network with point-to-point routes. If two ground stations on opposite sides of the Earth can both access the satellite network, communication between them can even be faster than via terrestrial networks, thanks to a faster light propagation in the vacuum of space. This animation shows the planned phase 1 of SpaceX's Starlink constellation, which is probably the most well-known. The animation is sped up by a factor of 8, but you can easily see how fast these satellites move in relation to Earth. At the lower altitudes, satellites have orbital periods of about 90 minutes, so each satellite completes a full journey around Earth in 1.5 hours. The different colors show different shells of the constellation. Each shell is a group of satellites of the same orbital parameters spaced evenly around the globe. Now, recently it has been proposed to bring edge computing to LEO communication networks as well. Edge computing brings compute infrastructure to the edge of the network, so data can be processed close to clients rather than in some distant central cloud data center. And the way this works is that edge computing platforms abstract from the heterogeneous distributed infrastructure so that developers can easily deploy their edge applications. Now, even though latency may not be a big issue in global LEO communications, sending all data to a central processing location over the network still puts a considerable strain on the satellite network. So the idea is simple. Let's add compute resources to the communication satellites that provide our internet uplink. But how will you as a developer possibly deploy your applications to tens of thousands of satellite servers? Well, what we need is a common LEO edge computing platform that abstracts from the underlying infrastructure, as is common with terrestrial edge computing as well. But what does that look like? When we think about such a platform, the first question that comes to mind is this: how will we organize applications? What form will they have? If we answer this question first, we can dive into all of the technical details. To reason about this, let's first look at our options. We consider different organization paradigms for applications, so OPAs, that have evolved in the past 2 years in the fields of cloud and edge computing. The general stack is the same across all paradigms. You have your hardware at the bottom, then you have operating system, your runtime, and applications. But over time, more and more layers became shared across different applications. So virtual machines, for example, share common hardware, but each have their own operating systems. Containers share an operating system, but each provide their own runtime. And serverless functions even share their runtime. Now, of course, the distinction is not actually that easy when you get down to the implementation details. For example, what are micro VMs or Unix kernels? Containers or VMs? What is OpenWhisk, a serverless platform based on containers? For now, we are only talking about general paradigms, not technologies. And to find out which organization paradigm makes sense for our platform, let's look at two things: the unique challenges of the LEO Edge on one side, and the requirements that users and applications have for our platform. Now, the LEO Edge is quite a unique environment. First, the satellites and with that satellite service are mobile. Remember how quickly those satellites orbit the Earth. Second, all the satellites are built equally. It doesn't make sense to put different hardware in one but not the other, since they are maybe at different places in a few minutes. And third, those satellites must be evenly distributed, so they can provide the same level of coverage, internet coverage at all times, even as they move around. However, the actual demand is heterogeneous. Think population centers where more clients access the network. Then given the price of launching hardware, satellite servers are likely to have limited compute capabilities. And speaking of launch costs, they're also not physically accessible for maintenance. And thus they can also not be upgraded without replacing them. And finally, we can only deploy servers where the satellites are. So we cannot just put an additional server somewhere for convenience without actually deploying a satellite. Let's look at the application requirements next. The point of edge computing is to make services available near clients, so that is a must. I want my applications to be deployed in physical proximity, so optimally at the satellite the client is currently connected. I also want my application to be highly available, even if one satellite fails. And if we have multi-tenancy, so multiple application providers running on the same platform, I want my application to be isolated from those other tenants. If possible, I also want to use a familiar and open tech stack, the same one as I use in the cloud maybe. And I want to deploy and update applications flexibly, maybe even as a pay-as-you-go model, as we know from the cloud. And finally, elastic scalability is important as well. If more users want to access my service, suddenly, I want to dynamically be able to add more resources to it. Now, for the sake of time, we're only going to look at the first requirement today, but you can, of course, find the detailed evaluation in our paper. So, as I've mentioned, satellites are inherently mobile. So ground stations frequently need to reconnect as satellites move out of reach, either because they orbit or because the Earth revolves underneath the constellation, which is another issue. So what we want is applications and data to follow along as reconnections happen. So they are always available at the closest satellite for a consumer. This is also referred to as virtual stationarity. We find that the migration overhead is lower when you move from VMs to containers and from containers to serverless function. And the reason for that is simple. The more layers of the stack you share, the less application-specific runtime and operating system details you have to move. But next to the application, there's also state data. That state is actually an important factor, as it limits my ability to deploy the copies of the same service simultaneously. Stateless serverless functions have an advantage here, because I can just redeploy them without migrating their current state. Instead, we have the option to move state to a shared serverless database, for example. Another hindrance to deploying applications close to clients is the mismatch between heterogeneous demand and homogeneously distributed servers. In terrestrial edge computing, I can just build my server where all my users are, but I don't really have that option here. We may need to offload some requests to close satellites instead of the optimal one to distribute spikes of requests. Again, how well we can do this is dependent on how easy we can migrate and replicate services. And again, stateful services make our lives a bit difficult here. This also raises an orthogonal question. How will we actually schedule edge service requests for load balancing? But that is a different topic now. This is just a small excerpt of the paper, and I encourage you to read our evaluation of the other requirements as well. For now, let me just conclude our findings. We found that our requirements for the best OPA for LEO edge computing platform are a low performance overhead, that we can flexibly reconfigure scheduling of services to nodes, support for mobility of application components, strong isolation for multi-tenancy, and we actually conclude in our paper that the serverless paradigm best meets those requirements. And this also opens up a lot of future work in the field. For example, we can now discuss technical details of a LEO edge computing platform. We can also think about how we would load balance and schedule requests, preferably without a centralized controller. And if we implement a prototype, how can we evaluate it without access to a proper satellite network? What will our edge applications actually look like? And how can we manage that state handoff efficiently? Again, let me thank you for having me at EdgeSys. My co-authors and I are excited to hear your thoughts on this topic, either on the EdgeSys Slack or via email.